Hi, today we will start our discussion on active filters. Uh, Active filters. Okay, we know that active filter includes capacitor, resistor, and active device, which is op amp, and the gain can be greater than 1, can be like less than 1 and greater than 1. So depending to different parameters of the circuit, the gain can be any value from negative infinity to positive infinity. So we did a review on DC op amp circuits. We know that an op amp has two inputs, non-inverting input, which is a positive terminal, and we show it with V sub P, and also we have inverting input, which we show with negative sign, and we show it with V sub N. We have output, and of course we have two external power supplies, plus VCC and minus VCC. And we know that the gain is very large number, like tends to infinity in like open op amp circuits with no feedback. And op amp has two characteristics. First, IN is equal to IP is equal to 0, so there is no current entering to inverting and non-inverting terminal. And the second rule in the op amps with feedback, op amps with feedbacks, so op amp with feedback, the op amp tries to keep Vn equal to Vp. Okay, so we have two important equations and rules here. The currents are equal to 0, and within the op amps with the feedback, the Vn is equal to Vp. So let's start our discussion on active filters by having one example. Let's say show the following circuit is a high pass filter with cutoff frequency of omega c is equal to 1 over R1 C, and pass band gain of negative R2 over R1. So let me make sure that it's recording. Okay, and here is the circuit. The capacitor has like an impedance of 1 over j omega c, of course, and we want to solve this circuit. The first thing we should do, we know that these two elements can be combined together, and we have z1 equal to r1 plus 1 over j omega c. Now Also, we know that Vn is equal to Vp. Vp is connected to the ground, which is equal to 0, is equal to Vn. Okay, now we write KCL at this node. Let's just call it node A. Okay, KCL at node A. The total currents leaving the node is equal to 0. So we can say Vn minus, oh, by the way, so the voltage source is Vs. Vn minus Vs over Z1 plus Vn minus Vo over R2 is equal to 0. We know that Vn is equal to Vp is equal to 0. So this one is 0 and this one is 0. So as a result, we will have Vo over Vs is equal to negative Z2, not Z2, R2, sorry, R2 over Z1, which is equal to negative R2. Instead of Z1, we put R1 plus 1 over J omega C. This fraction is equal to negative J omega R2C over 1 plus J omega R1C. How do I know this? It's very easy, it's very simple. So we said that it's equal to negative R2 and J omega C over R1 J omega C plus 1. And so this one is equal to negative J omega R2C over 1 plus J omega R1C. Let's factor out, not factor out, let's just write it in this way. R2 negative R2C times J omega. For the denominator, we want to factor out R1C. You might ask how we are going to factor out R1C from 1, so it's easy. We can say R1C times 1 over R1C plus J omega. Okay, so if we multiply this R1C by 1 over R1C, we get 1. And if we multiply R1C by J omega, we get J omega R1C. Okay, so C will be cancelled by C. We will have it's equal to negative R2 R1 times J omega over J omega plus 1 over R1C. Why we separated R2 over R1 from this fraction? Because R2 over R1 is like constant. It's not frequency dependent, but the second parenthesis is frequency dependent value. Okay. Now we can say at DC frequency, DC signal, or omega is equal to 0. We know that the magnitude of Vo over Vs is equal to 0. Why? Because this one is equal to 0, and 0 times any other value becomes 0. And as omega goes to infinity, VO will be equal to negative R2 over R1. How do we know this? If omega goes to infinity, this value will be negligible compared to j omega, because j omega will be much more greater than 1 over r 1c, so we can like ignore this one. So j omega over j omega gives 1, and so the gain will be negative r2 over r1. Okay, so based on what we see here, for omega 0, gain is 0. For omega is infinity, gain is negative r2 over r1. And this one is a characteristic of a high pass filter. Okay, high pass filter, because for low frequencies the signals are blocked. Okay, and for high frequencies the signals are allowed to pass. Now we want to determine the cutoff frequency. So cutoff frequency, we need to determine the cutoff frequency in which gain falls to 1 over square root of 2, or 0.707 of maximum gain. Here is very important point, maximum gain. So negative r2 over r1 is maximum gain, so we should reach to 0.707 of maximum gain, which is negative r1 over r2. How we can do that? We know that the magnitude of the gain is the magnitude of this value, negative r2 r1 j omega over j omega plus 1 over r1c. Okay, so r2 r1 are constant numbers, so we don't like the magnitude the same as the value, so it's the same. But for this part, because it's a like complex number, we need to find the magnitude. So square root of 0 plus omega 2 over square root of omega 2 plus 1 over r1c square is equal to, by the way, because we like talking about this, like the magnitude, we consider like we remove the negative sign because we just talking about the absolute value, so we show it with positive. Okay, because we talk about like the amplitude regardless of the size, the sign, sorry, regardless of the sign. So it's equal to r2 over r1 omega square root of omega square plus 1 over r1c square. Okay, we can say that the value of omega that makes the output equal to 0.707 of the maximum occurs at 1 over R1C. How do we know? Let's just see. Let's just double check. VO over VS at frequency of 1 over R1C is equal to R2 over R1. Instead of omega, we put 1 over R1C. Instead of omega square, again, we put 1 over R1C square plus 1 over R1C square. Okay, which is equal to R2 over R1, 1 over R1C, square root of 2, 1 over R1C square, which is equal to R2 over R1, 1 over square root of 2, or we can say it's equal to 0.707 R2 over R1. So at the frequency of 1 over R1C, we saw that the gain is 0.707 times the maximum value. Let's just graph the frequency response of this filter. Omega gain, which is equal to VO over VS. For gain infinity, we had R2 over R1. This one is like the magnitude. It's not the like real the whole. It's not the like the complex value of the gain. It is the amplitude of the gain. So it's the reason why we consider it as a positive number. So here it's 1 over square root of 2 of R2 over R1. Let's like mark these two area. And if we assume here is omega C, we can say that the signal should be something like this. Okay, or it's a better way. Let me just, for example, like this. Yeah, it's better. So this one is the frequency response of this filter. And as you see, what's the difference between this filter and the passive high pass filter that we saw in the previous lecture? It's a big and previous lecture we knew that the gain is less than 1, but here the gain is negative, is R2 over R1, and it can be any value. Okay, so the other thing, if we have this circuit and without solving the circuit, if somebody asks us what kind of filter is this filter, if you remember, we did the same trick for passive filters. Can we find out the type of the filter by just looking to the circuit? Of course, yes, because we know that capacitor ZC is open circuit for omega 0, and ZC is short circuit for omega is infinity. Using this simple rule, we can easily say that if this filter is high pass filter or low pass filter, if the frequency is 0, here is open circuit and there is no path between input and the output. So output will be equal to 0. There is no path between input and output. So for a 0 frequency, the output is equal to 0. Okay, what about frequency of omega? For infinity or frequency, we know that the filter acts like short circuit and there is a connection between input and output. So we have a signal at output. Okay, so we have VO, which is not equal to 0. So based on these facts, we can say that this filter is a high pass filter, not a low pass filter, because for low frequencies output is 0. For high frequency we have some output. What is the value of that output? We don't know, just we can figure it out by solving the circuit, which we did, and we got the answer, which was negative R2 over R1. Okay, so next let's move to the next example and see one more circuit example. Part A, show the transfer function T of j omega, which is of course VO of j omega over Vs or Vin of j omega. Transfer function showed the transfer function has low pass gain characteristics. Part B, select element values so the passband gain pass band gain is -4 and cutoff frequency omega c is 100 radian per second. Okay, we know that omega is 2 pi f, so frequency will be 15.9 hertz. So here we are designing actual filter. Okay, we are going to design actual filter with a specific gain and cutoff frequency. So it's very good. We are able to design an actual filter that blocks the frequency below any frequency we want, which here is 15.9, and also we can define the gain of this filter. Let's see how we can solve the circuit. First of all, let's see the circuit itself. So the circuit is, of course, an op amp. Non-inverting terminal is connected to the ground, and the inverting terminal is connected to voltage source, which is here, and Vs is input voltage, R1 is here, and the feedback consists of two elements, one resistor and one capacitor in parallel, and at the output we have of course VO, and of of course, this resistor should be R2, and the capacitor is 1 over j omega c. So let's solve this problem. So for this part, we just call it R1 is equal to Z1, and these two together we call it Z2. Okay, so Z1 of course is equal to R1. What is Z2 is equal to R2 in parallel with 1 over j omega c. Let's find it out. It's equal to R2 over j omega c over R2 plus 1 over j omega c, which is equal to R2 over 1 plus j omega R2c. So this one is Z2. So we have Z1 and Z2, and the next thing we should do, it's simple, Vp, Vn. We know that Vp is equal to 0, so we say Vp is equal to 0 is equal to Vn, and we write KCl at point A, KCl at point A, at node A. So we can say Vn minus Vs over Z1 plus Vn minus Vo over Z2 is equal to 0. Okay, so we got the KCl, and we can solve this KCl to find the gain of our filter. Okay, so what we can do here, we simply say Vn is equal to 0, Vn is equal to 0. So as a result, Vo of j omega over Vs of j omega is equal to negative Z2 of j omega over Z1 of j omega. These j omegas in the parentheses means that the complex values, okay? So it's not magnitude, it's just whole value, so it's the complex number. As a result, we can say T of j omega is equal to Vo of j omega over Vs of j omega is equal to negative. So if we divide Z2 by Z1, Z2 is here, Z1 is here, so definitely it will be equal to negative R2 over R1 times 1 over 1 plus j omega R2c. So this one is the value. Now we simply can see the characteristic or behavior of this filter. So if omega is 0 or DC signal, we can see that T of j omega is equal to negative R2 over R1, because inside the parenthesis will be equal to 1. For omega equal to infinity, this fraction will be equal to 0, so the entire gain will be equal to 0. So T of j omega is equal to 0. So if we look here, we see that for low frequency we have a signal which is equal to negative R2 over R1, and for high frequency we have no signal, and all signals have been like blocked. So this is a characteristics of a low pass filter. Okay, now it's time to find the values of the elements, like values of elements. So the passband is -4 and the cutoff frequency is 100 radian per second. How we can do that? It's very easy. Part B, the gain, the value of gain this time, which is VO over VS, is equal to the absolute value of negative R2 over R1 time 1 over 1 plus J omega R2C. Okay, it's equal to R2 over R1 1 over square root of 1 plus omega R2C square. So, where is the cutoff frequency? The cutoff frequency is frequency that this term is equal to square root of 2. So, definitely at omega equal to 1 over R2C, we will have the square root of 2 in this equation. So, when we can say when omega is equal to 1 over R2C, VO over VS or Vin is equal to R2 over R1 1 over square root of 1 plus 1 over R2C square, which is equal to 1 over square root of 2 R2 over R1, or we can say it's equal to 0.707 R2 over R1. So, cutoff frequency is omega C is equal to 1 over R2C. That's the first part. Okay, first part. We want to have this cutoff frequency equal to 100, but we have two variables. Okay, so we want to get 100 here, but we have two variables. Let's stop here and move to the gain part. The gain part. So for the gain, we can say we want gain equal to -4. -4. Okay, we know that the maximum gain VO over VS is negative R2 over R1, as we saw here. Here, the maximum gain is negative R2 over R1, and we want to have this value equal to -4. So R2 so R2 should be equal to 4R1. R2 should be equal to 4R1. Okay, so let's just pick a value for R1 based on our component availability. So let's say let's choose um, R1 is equal to 10k, 10 kilo ohm. Okay, so if R1 is equal to 10 kilo ohm, we can conclude that as a result R2 should be equal to 40 kilo ohms. R R2 should be equal to 40 kilo ohms. So we have now, so we picked R1 by ourselves, so we could pick any value. So let's say if we picked R1 is equal to 1 kilo ohm, so we conclude that R2 should be equal to 4 kilo ohm. As long as this relationship between R1 and R2, this, let me just write it again, R2 is equal to 4R1. As long as this relationship is true, no matter what is the value of the elements. So let's just consider the 10K and 40K. So far we have R1 equal to 10 kilo ohms and R2 is equal to 40 kilo ohms. Okay, so based on these values, gain is negative 4. What about the cutoff frequency? We want omega c equal to 100, which we know that omega c is equal to, we already calculate the value of omega c, 1 over r to c should be equal to 100. So as a result we can say c, the capacitor, should be equal to 1 over r2 times 100, r2 times 100, or 1 over 100 times 40k. If we calculate this value, C will be equal to 0.25 microfarad. Okay, so we designed our own filter. So if R1 is 10k, if R2 is 40k, and if C is 0.25 microfarad, we will have a low pass filter. We will have a low pass filter with cutoff frequency of 100 radian per second and gain of negative 4. Okay, so here is the circuit we have. So let's just draw the complete circuit. So we should have this circuit. Let me just show the circuit. uh, let's just build this circuit, for example, in the lab. Okay, if we build this circuit in the lab, we need to have an op amp and use this configuration to have a low pass filter with the cutoff frequency of 100 ohms, 100 radian per second, and gain of, okay, this one is a circuit. I'm sorry, like I know it's like messy, but I don't know what's wrong with my pen. So uh, If we draw the frequency response, omega gain, here is R1 over R2 or R1, which we know that it's 4, and here is 0.707 times 4. Here is omega c, which is 100 radiant per second, and here is the signal. This one is the frequency response of this filter. Okay. Now we move to the next example, which in fact design is like a passband filter, and we want to characterize that filter. So let's do that together. Let's say this example, which is the last example for active filters. We want to solve this problem for the following circuit. Find input output relationship VO over VS. Then for R1 equal to 1 kilo ohm, C1 is equal to 0.1 microfarad, R2 equal to 10 kilo ohms, and C2 equal to 1 microfarad. Plot the frequency response and discuss the characteristics. Okay, so here we have a filter which different parameters are given, and we want to plot the frequency response. Let's see the circuit. First, let me check if it's recording. Yes, of course. And so here is the filter. We have an op amp. Okay, this one is the circuit. So how we can solve this circuit? The first thing, we should define Vn and Vp. Vp gets the feedback from the output, so we don't know what's the value of Vp, but Vn is definitely known. because as we know the current here is 0 and the voltage across the capacitor is the Vn. So how we can determine the voltage across this capacitor using a voltage division. Okay, so that's simple. So we can simply say Vn is equal to the impedance of the capacitor, which is 1 over j omega C1, over the total impedances, which is R1 plus 1 over j omega C1 times Vs. Okay, now what is VO? If we look to this part of the circuit, we see that here is VP, VO is equal to VP, it's short circuited to VP, not VO, sorry, the output of the op amp, not VO. The output of op amp is connected to the VP, so it's a VP. So we have a value here, and we want to find the voltage across the resistor. And again, the same voltage division. The voltage across this resistor R2 is equal to R2 over the total impedances times Vp. Okay, so we can simply say VO is equal to R2 over R2 plus 1 over J omega C2 times Vp. Okay, we know that Vn is equal to Vp, so we substitute this value here. Okay, and as a result, we will have VO is equal to R2 over R2 plus 1 over J omega C2 times 1 over j omega C1 over R1 plus 1 over j omega C1 times Vs. Okay, which is equal to j omega R2 C2 over 1 plus j omega R2 C2 times 1 over 1 plus j omega, let me see, R1 C1, R1 C1. So times Vs. And then we can say VO over Vs is equal to, from the first parenthesis here, we from numerator and denominator we factor out R2C2. So we have R2C2 times j omega. In the denominator we say R2C2 times 1 over R2C2 plus j omega. So for the first parenthesis, for the second parenthesis, we for numerator we keep 1, and for denominator we factor out R1 C1, so it's equal to 1 over R1 C1 plus j omega. Okay, now that we have these equations, we can simplify them. So this one is cancelled with this one. Okay, and what else we can do? we let's see what we can do. Okay, we bring this R1C1 from denominator to the numerator and write it in this way. VO over VS is equal to J omega over R1 over R2 C2 plus J omega times 1 over R1 C1 over 1 over R1 C1 plus J omega. Now that we got to this point, we can simply calculate the gain. Gain is equal to absolute value of VO over VS, which is equal to, for the first bracket, we know that the amplitude of J omega is omega. For the denominator, we can write it like this: square root of 1 over R2 C2 square plus omega square. This one is the first parenthesis, the first term. R2C2. Okay, the second term will be the numerator is a constant value, so it's 1 over R1 C1, and denominator is square root of 1 over R1. Oh, just wait a second. I need to wait a few seconds for my pen to fix. Okay, let's try to see if it's working. Square root of 1 over R1 C1 square plus omega square. Okay. Now that we have this gain, we need to discuss the characteristic and find the different parameters. If frequency is 0, if the frequency is 0, this value is 0, so entire gain will be equal to 0. So if omega is 0, VO over VS is equal to 0. If omega is equal to infinity, what's going on? If omega is equal to infinity, second parenthesis will be equal to 0. So again, the total gain will be equal to 0. So for low frequency, the gain is 0. For high frequency, the gain is 0. What kind of filter is this filter? It's definitely a band pass filter. Okay, so it is a band pass filter. Let's just find the cutoff frequencies. Okay, cutoff frequencies. So if omega is equal to 1 over R1 C1, which is equal to 1 over, what was the value of R1? R1 was 10 to the power of 3. C1 was zero point 0.1 times 10 to the negative 6. If we multiply these values, it should be equal to 1000 over 0.1, 10 to the power of 4. So it's 10 to the power of 4. If omega is 10,000, the gain is equal to 0.9999 times 1 over square root of 2, which is 0.707. This one is the first cutoff frequency. The second cutoff frequency, we can say if omega is 1 over R2C2, which is equal to 1 over, what is the value of R2? 10 times 10 to the power of 3 times C2, 1 microfarad, 10 to the negative 6, which is equal to negative 3, negative 2, so 100. So it's 10 to the power of 2. Okay, if omega is equal to 10 to the power of 2. As a result, VO over VS will be equal to 1 over square root of 2 times 0.9999, which is almost equal to 0.707. Okay, so these two are cutoff frequencies, and let's graph the frequency response. Omega, here is 0.707, here is 1, here is 10 to the power of 2, here is 10 to the power of 4. So like we should just scale a logarithmy, and let's see. Okay, so mark these lines. Okay, and this one will be the frequency response of this filter. So here is bandpass filter range, and the other areas are stop band. And we call this one 10 to the power of 4, we call it cutoff frequency high, and 10 to the power of 2 is cutoff frequency low. So by looking to this graph, we can say that frequencies less than 10 to the power of 2 radian per second and higher than 10 to the power of 4 radian per second are decreased or blocked, or we can say blocked. Frequencies between 10 to the power of 2 and 10 to the power of 4 can pass through with little or no attenuation. Okay, so this one was the active filter discussion and lecture, and we will continue our AC signal systems with the next lecture. Thank you.